Far beyond the coastline, where waves rise and fall like breathing steel, massive wind turbines float silently across the open ocean, spinning energy out of air and salt water. These are offshore floating wind farms, the newest frontier of renewable power, and one of the most complex engineering challenges humanity has ever attempted. Welcome to the How Factory, where today we'll uncover how these colossal machines are designed, built, and anchored in some of the harshest environments on Earth. Producing electricity miles away from shore sounds simple. Just put a turbine in the sea, but the process behind it is a masterpiece of precision, logistics, and ingenuity. Every component, every cable, every bolt must survive decades of storms while generating clean energy for millions of homes. It all begins long before the turbines touch the water, in massive shipyards and factories scattered across the world. Engineers start with digital models, mapping the exact conditions of the chosen ocean site: wind speed, wave height, current direction, seabed depth. These measurements determine what type of floating platform will hold each turbine upright, and that's where the magic begins. Unlike traditional offshore wind farms, which bolt towers directly into the seabed, floating wind farms rest on buoyant platforms tethered by heavy anchors and chains. These floating foundations come in several designs: spar buoys, semi-submersible pontoons, and tension leg platforms. Each has its own purpose depending on depth and wave activity. A spar buoy looks like an enormous steel cylinder, hundreds of feet long, weighted at the bottom so it floats vertically like a giant nail in the sea. Semi-submersibles use wide, triangular bases of interconnected pontoons that spread out weight evenly, while tension leg systems rely on taut cables that hold the structure firmly in place even as waves crash around it. These foundations are built onshore in specialized yards, some as long as aircraft runways, using reinforced steel and marine-grade concrete. Workers weld, coat, and seal each section to resist corrosion from salt water and pressure. The scale is staggering. A single floating base can weigh more than 5,000 tons before the turbine is even added. Once the base is ready, attention turns to the turbine itself, the towering white structure that captures wind energy. Each turbine stands up to 250 meters tall, from sea level to blade tip, with blades longer than a football field. Inside the nacelle at the top is a generator capable of producing several megawatts of electricity. These components arrive in pieces: blades from one factory, the nacelle from another, and the tower sections from steel mills around the world. Assembly happens in coastal yards, where heavy lift cranes maneuver each piece into place. The entire structure is pre-tested for balance and wiring before it ever meets the ocean. When it's complete, the finished turbine is carefully lowered onto its floating foundation. Connecting the two is one of the most delicate moments in the process. Engineers use massive hydraulic jacks and GPS-guided systems to align bolt holes with millimeter accuracy. One wrong move, and months of work could be lost. After the turbine and platform are joined, it's time for launch. Because these giants are too large for land transport, the entire unit is floated out to sea using semi-submersible heavy-lift ships or tugboats. The operation is slow, precise, and weather-dependent. Crews wait for perfect calm before towing begins. Once afloat, the structure moves at barely a walking pace, escorted by support vessels carrying engineers and divers. Navigation is guided by satellite, ensuring the turbine reaches its exact coordinates, often dozens of miles offshore. When it arrives, underwater robots, known as ROVs, spring into action, attaching massive chains or steel cables to anchors embedded in the seabed. Each anchor can weigh more than 100 tons and is drilled deep into sand or rock for stability. The mooring lines keep the platform secure while allowing it to move slightly with waves and tides. It's a balance of flexibility and strength that defines the art of floating design. Next comes the invisible but vital link: power cables. Thick armored cables, sometimes 20 centimeters in diameter, connect each turbine to a central offshore substation. Inside these cables, copper and aluminum conductors carry electricity, while multiple layers of insulation, steel sheathing, and waterproofing protect them from the brutal ocean environment. Installation requires specialized cable-laying ships that unwind coils of cable across the seabed, guided by sonar and GPS to avoid twists or damage. Once connected, all the turbines feed their power to the substation, which transforms the voltage for transmission to shore through a single high-voltage export cable. On land, this energy flows into the main electrical grid, clean, renewable, and nearly silent. Building one turbine is challenging enough, but a full floating wind farm can involve dozens of them, each generating hundreds of megawatts. Coordinating this construction is like conducting a global orchestra. Steel for the platforms might come from South Korea, cables from Norway, and turbines from Europe or the US. Every stage must align perfectly. Delays in one component can idle ships costing hundreds of thousands of dollars per day. Logistics teams plan years in advance, scheduling transport, weather windows, and on-site crews down to the hour. And because these projects happen offshore, every piece of equipment, from wrenches to welding rods, must be shipped out on supply boats. There's no hardware store in the middle of the ocean. Safety and maintenance are constant concerns. Engineers designed floating platforms to survive waves as high as 10 stories and winds stronger than hurricanes. Sensors monitor stress, tilt, and vibration in real time, sending data back to control centers on shore. Drones and autonomous boats now perform visual inspections, reducing the need for risky human climbs. Some systems even feature self-stabilizing turbines that adjust their orientation to reduce stress during storms. The goal is longevity. Each turbine must operate for 25 to 30 years with minimal downtime. Economically, floating wind farms are changing the game. Traditional offshore turbines are limited to shallow waters, but floating systems can operate in depths over 1,000 meters, opening vast new regions for clean energy. From the coasts of California and Japan to the deep North Atlantic. These deeper waters often have stronger, steadier winds, meaning higher power output. As technology improves, costs are falling fast, approaching parity with fossil fuels. Governments and companies worldwide are investing billions into this new frontier. A single floating wind farm can power 500,000 homes. Environmentally, the benefits are enormous. Offshore wind produces zero emissions once built, and floating foundations disturb far less seabed than fixed platforms. Many designs allow marine life to thrive underneath, turning turbine bases into artificial reefs. The turbines are quiet enough to avoid harming most marine species, and projects undergo extensive ecological studies before approval. Some researchers are even exploring ways to integrate seaweed farming and aquaculture alongside wind farms, creating multi-use ocean zones that generate both food and energy. Of course, challenges remain. Saltwater corrosion, extreme weather, and the logistics of deep-sea maintenance push engineering to its limits. Building and towing giant structures across open oceans requires precision timing and enormous ships. But with each new installation, the process becomes smoother. Early projects like High Wind Scotland proved the concept. Now, commercial-scale farms in Asia, Europe, and the US are setting new records for size and efficiency. The future may see fully automated floating wind farms managed by AI and serviced by autonomous drones. Clean energy ecosystems that operate day and night without human presence. In the grand scheme, floating wind farms represent more than just turbines. They're a symbol of possibility, proof that human innovation can adapt even the wildest parts of nature to sustain us responsibly. From the first steel plates welded in a coastal yard to the moment a turbine catches its first gust offshore, every step reflects the best of modern engineering. Strength, balance, and respect for the planet. So the next time you see a distant row of white blades turning on the horizon, remember what lies beneath. The anchors gripping the seabed, the cables humming with power, the teams coordinating from ship to shore. These are not just machines in the ocean. They are monuments of progress, floating silently on the waves, harnessing the wind to power the world. That's how offshore floating wind farms are constructed in the ocean. A blend of science, scale, and sustainability that's redefining the future of energy. Thanks for watching The How Factory, where we uncover how the world really works. Don't forget to like, subscribe, and join us for more stories of innovation, engineering, and human ingenuity shaping our planet's future.